So let's say we've got some buffer situation here. I've got a weak acid and it's in the same solution with a substantial amount of its conjugate base. And I'm just going to make these numbers up. And so the numbers, let's say initially we've got 0.15 molar, and here I've got, we don't know what that is yet, and here I'll just make that 0.10 molar. We'll have a change, and the change is the reaction is moving to the right. It has to. We're going to ionize to a very small degree. The weak acid will have plus X here, and we'll have plus X here. And at equilibrium, we're going to have 0.15 minus X. 0 plus X is X, and 0.1 plus X. Let's say the Ka of our solution, we'll make this acetic acid, and the Ka for acetic acid is 1.8 times 10 to the minus 5. Now, we can go ahead and make the assumption that X is small relative to their starting concentration, so that simplifies our problem a lot. And we can build our equilibrium constant expression, which is going to be Ka is equal to H plus times the anion in our buffer system divided by HA. And if I solve for hydrogen ion, this is what that's going to look like. I'm going to go ahead and multiply both sides by the Ka, so I'll have Ka times the HA, the weak acid concentration, and then I'll divide that by the weak base, its conjugate base concentration, and that equals H plus. So I've solved for H plus. I can simply plug those numbers in, solve for H plus, and get the pH from that H plus concentration. So we'll go ahead and we'll solve for the pH of the solution by taking the negative log of the hydrogen ion concentration. Let me clean that up a little bit. And that's going to give us the pH. So let's go ahead and plug our numbers in. That's going to be 1.8 times 10 to the minus 5 is equal to X times the weak base concentration, which we said was 0.10, divided by the weak acid concentration, which we said was 0.5. We'll go ahead and solve for X, which is the hydrogen ion concentration. So the hydrogen ion concentration will equal 1.8 times 10 to the minus 5 times 0.15, and then we'll divide that by 0.10, which was the anion concentration. And that gives me, looks like 2.7 times 10 to the minus 5 molar. Minus 5 molar, that's in hydrogen ion. I'll go ahead and get the pH by taking the negative log. We know that's going to be a little less than 5 of 2.7 times 10 to the minus 5, which gives us 4.57. Okay, so that gives us a pH of 4.57. So that's the long way around to solving for the pH of a solution. There is an easier way to solve for the pH of a buffer solution. Now, this only works for a buffer solution. What I'm going to do is I'm going to take the negative log of both sides of this equation. Okay? When I do that, I got pH, and I'm going to employ some log rules here. pH is equal to the pKa, that's the negative log of the Ka, and that gives me minus the log of the acid concentration over the base concentration. Now I'm going to use my log rules here to change this a little bit. All I need to do to turn this negative sign into a positive is to invert my acid and weak conjugate base. And when I do that, I get pH is equal to pKa plus the log of the base over the acid concentration. This is the Henderson-Hasselbalch equation, which is right here. Now we're going to go ahead and plug the numbers in, make sure that it worked, just so we can prove that to you. So here's what we've got. We've got the negative log of the Ka, so this is the negative log of 1.8 times 10 to the minus 5, which gives me 4.74. That's the pKa. And then plus, we've got the log of the concentration of the base, which was 0.10, and the concentration of the weak acid, 0.15. So we'll add that, plus the log base 10 of 0.1 divided by 0.15. And when I do that, I get exactly the same answer, 4.57. Okay, 4.57. That pH matches the pH that I got with the ice table. Now, the ice table works just fine. It just takes longer. Now, I want to keep this in mind. You can only use Henderson-Hasselbalch for a buffer. Doesn't work for a weak acid or a weak base ionization. It has to be a buffer where you have substantial concentrations of both weak base and weak acid. So this equation can take a variety of forms, so be careful when watching tutorial videos from other sources. Be sure you know what each term represents. And you can also use an ice chart, but this equation is usually faster, especially if the problem has repetitive parts. So there we go. Okay. Example, buffer pH. Calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.20 molar sodium benzoate using an ice chart. So I had to look up the Ka for benzoic acid. I just went online, and I have 6.3 times 10 to the minus 5, relatively small. So using an ice chart. Now, even if you don't know the formula for benzoic acid, this is just our symbol, Ha, for a generic weak acid. You don't need the actual formula, and it saves time. It's going to ionize to a small degree, produce a little bit of H plus a little bit of A minus. The only thing is, this is a buffer. It's not, we don't get our anions simply from the ionization of the weak acid. That's actually going to be suppressed because I have, along with 0.12 molar of the weak acid, I have a 0.20 molar concentration of sodium benzoate. So if I were to just sort of symbolically show you what that looks like, it's a completely soluble, strong electrolyte. It's going to produce a little bit of sodium cation and anion. So this is 0.20 molar. This will also be 0.20 molar, and that's how I made my buffer. So this will be my initial, my change, and equilibrium. And I want you to notice how much time it takes to actually perform this experiment. We're going to have minus x plus x plus x. We add the initial to the change line. We get 0.12 minus x, that is an x, and 0.20 plus x. Now, this x and this x will be small enough to ignore. We've got 4 orders of magnitude difference between both the initial concentration of the acid and the base, and 4 orders of magnitude is on the order of 10. The Ka is 10,000 times smaller than the initial concentrations. This x is going to be insignificant. So we'll go ahead and we will ignore those x's. We'll write our equilibrium constant expression, which is Ka equals H plus times A minus divided by the concentration of your weak acid. We'll go ahead and symbolically solve for H plus, there we go, which is equal to the Ka times the weak acid concentration divided by the weak base concentration. All right, let's go ahead and let's solve the problem. Since we've already arranged our equation to solve for the hydrogen ion concentration, which is X, we can say X, which is equal to our hydrogen ion concentration, is equal to the Ka, 6.3 times 10 to the minus 5 times my HA concentration, which is 0.12 molar, divided by my weak base concentration, which is 0.20 molar. Let's go ahead and plug that in the calculator. So that's going to be 6.3 times 10 to the minus 5 times 0.12. That's my HA concentration divided by 0.20, my weak base concentration, and I get 3.78 times 10 to the minus 5. So X, which equals the hydrogen ion concentration, is equal to 3.78 times 10 to the minus 5 molar, and that's in hydrogen ion concentration. So now what I want to do is I want to go ahead and I want to take the negative log to get the pH, and you know it's going to be a little bit less than 5, so there'll be the negative log of 3.78 times 10 to the minus 5, and when I take the negative log of that, I get 4.42. So my pH is equal to 4.42. All right, that's using an ice table. So what we're going to do is we're going to show you the advantage of using the Henderson-Hasselbalch equation with the same value. So let's go ahead, write the Henderson-Hasselbalch equation. It is, we derived it last time, pH is equal to pKa plus the log of, you got to remember this, it's base over acid. Okay, now we're just going to plug the numbers in. The only calculations I really have to do here are this. pH is equal to the negative log of the Ka, which is 6.3 times 10 to the minus 5 plus the log of base, and the base was 0.20 molar. The acid concentration was 0.12 0.2 molar. And here we go. So that's going to be negative log 6.3 times 10 to the minus 5 plus the log of 0.2 divided by 0.12. And that gives me 4.42, same as before. Now, I didn't time myself, but it is considerably, there's considerably less writing involved, considerably less work involved, and it does take a lot less time. You can knock out the Henderson-Hasselbalch equation if you know what you're doing in short